So let's take a look at some problems where we are going to determine whether or not some triangles are similar. So we're going to be using those similarity shortcuts that we took a look at in our last video, which, just to remind ourselves, let's just list out what those three shortcuts were. We had angle-angle similarity, which is where if we can show that two angle pairs are congruent between the two triangles, then the triangles are similar. We had side-side-side similarity, which is where if we make ratios of corresponding sides, we make a ratio for each pair of corresponding sides, and all of those ratios end up being equal to each other. That means that the sides are proportional, which is what we need for side-side-side similarity. And then we had side-angle-side similarity, which is where we have one pair of congruent angles, and then the corresponding side pairs on each side, what we call the sides that include that angle, those side pairs are in the same ratio, or those ratios, we make the ratios out of the corresponding sides and the ratios end up being equal to each other. Then that's side angle side. So in this first picture, it says triangle ABC has angles whose measures are 60 and 62. Triangle DEF has angles whose measures are 58 and 62. Is triangle ABC similar to triangle DEF? Well, at first glance, we look at this and we say, oh no, because they only have one pair of congruent angles, right? Just the two angles that are 62 degrees. They're the only ones that are congruent. So our first instinct might be to say, no, they're not similar because there's only one pair of congruent angles and we need two. But let's take a look if we put those angle measures in these triangles. So let's say triangle ABC. Let's say angle A is 62 degrees, and let's say angle B is 60 degrees. And then in triangle DEF, let's say angle D is 62 degrees, and angle F is 58 degrees. Well, what about these third angles? What would their measure be? We know that all three angles need to add up to 180. So if I just do 60 plus 62 to get 122, and then I do 180 minus 122, I get 58 degrees, which means angle C here is 58 degrees. And now we can see angle A is congruent to angle D, angle A is congruent to angle D, and angle C is congruent to angle F. So I have both pairs of angles that I need to be congruent, so we can actually say yes. Those are similar. Yes, triangle ABC is similar to triangle DEF by angle-angle similarity. In this example, we see another couple triangles here, and we have information about their side lengths. In triangle ABC, the length of A, which is corresponding to segment BC, that's a 3. B is 4, and C is 6. Well, first of all, we can see that this triangle is not drawn to scale from what it says up here, because it kind of clearly looks like this side is longer than this one, but hey, we go with what the numbers are that they give us. So we have 3, 4, and 6. In triangle DEF, we have these lengths. D is 9, E is 12, and F is 18. So our question is, are these two triangles similar? So we can look at this similarity statement and we can see the ratios of these sides that we should try to be making, because remember, the order of these letters is kind of important. So according to what that similarity statement says, we want to pair up AB and DE in a ratio and see if it's equal to BC over EF. And if you're not seeing where I'm getting these pairs, it's first and second letter, A, B, D, E. Second and third letter, BC, second and third letter, EF. And that leaves first and third letter, AC, paired with first and third letter, DF. So I want to check to see, do these three ratios actually equal each other, right? I'm checking for side-side-side similarity here. So now let's substitute in the actual values for each of these side lengths. AB is 6, and DE is 18. BC is 3, and EF is 9. AC is 4 and DF is 12. So now the question is, do all three of these ratios equal each other? So now I'm going to go into I'm going to go into fraction simplification mode, and I'm going to look at 6 over 18, and I'm going to realize I can divide both of those numbers by 6, and that's going to give me 1/3. 3 over 9, I can divide both of those numbers by 3, and that gives me 1/3. 4 over 12, I divide both those numbers by 4, and it gives me 1/3. So I can see that yes, actually all of these ratios are equal to each other. And that leads me to say that yes, triangle ABC is similar to triangle DEF by side-side-side similarity. Now some of you might have been able to do this a little bit differently. You might have looked at these numbers and said, wait a minute, 6 times 3 gave me 18. 3 times 3 gives me 9, and 4 times 3 gives me 12, which is fine. That's another way you could do a problem like this. Basically, you're checking for that scale factor that says that this shape is an enlargement of this one by a scale factor of, in this case, 3. All the side lengths got tripled in length to turn this triangle into this one. And so that scale factor of the dilation was 3. And it worked for all 3 sides. So that means, that we have proportional side lengths is what that is. Another way of saying what we just said there. So we can do this, we can make these fractions up, or we can look for that common scale factor that turns this number into this one into this one, and this one into that one. Now we have an example that I think is a little bit trickier. It says, are triangles PQS and RQP similar to each other? Now I think that's a little bit hard to see, so I'm going to outline those two triangles in 2 different colors. Triangle PQS I'm going to outline in yellow here. Okay, so we're looking at this triangle. And then triangle RQP I'm going to outline in a green color. Now we're going to have some overlap here, so I'll try and make it so that we can see both colors. So we're looking at those 2 triangles. Now, we have our 3 options for proving them similar, right? We know that we can use angle, angle, we can use side, 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 or we can use side, angle, side. And kind of the key is to look at, I think the key is, look at how many sides of each triangle you know the lengths of. So, for instance, in the yellow triangle, PQS, I know that PQ equals 18, and SQ equals 27, just 15 plus 12. And then in the other triangle, RQP, I know that one side is 12 and one side is 18. So the fact that they're only giving me information about 2 sides of each triangle would kind of guide me towards possibly using SAS, because I know for this one I need all 3 sides, and I know for this one I don't really need any sides. So although it's possible we would be using angle, angle, I think the fact that they're giving us lengths of 2 sides on each triangle is kind of guiding us towards maybe checking to see if SAS works. Now, of course, what we need is that pair of angles that would be congruent between the 2 triangles. So we don't have any markings that are showing any angles congruent between these 2 triangles. We don't have any specific angle measures that are given for any angles in the 2 triangles. But what I do notice is that both of those triangles are using that angle right there. Angle Q, basically, angle PQR or PQS, whichever name you want to give it. They're both using that angle. So that means that we can say that angle Q is congruent to itself, which gives us this one pair of angles that we need between the 2 triangles. So now the next thing we need to do is we need to look and say, do we have the side lengths for both triangles, the sides that include that angle in both triangles? Do we have those side lengths? For the yellow triangle, that angle is made up by SQ, which we know the length of, and PQ, which we know the length of. In the green triangle, that angle is made of RQ, which we know the length of, and PQ, which we know the length of. So now the question is, can I set up this ratio of corresponding sides and it ends up being equal? So I'm going to pick, first of all, I'm going to look at my yellow triangle, and I'm going to pick out the shorter of the 2 sides I know for the yellow triangle, which is the side that is 18 units long. That's PQ. All right, so PQ. And I'm going to pair that up with the shorter of the two sides that I know for the green triangle, which is RQ. Now some people want to pair up PQ with PQ, but in this case actually in the green triangle, RQ is the side that we want to pair up with PQ in the yellow triangle. And I know that again because PQ is the shorter of the two sides that I know, and RQ is the shorter of the two sides that I know on the green triangle. So I'm pairing up PQ with RQ, which is going to be 18 over 12. And now in this other ratio, we're going to basically pair up the longer of the two sides in each triangle. Now I have to be consistent here. This 18 was PQ, which I was looking at PQ being used on the yellow triangle, so I put that on top. So this other number here has to be the longer of the two sides on the yellow triangle in my picture, which is SQ, which has a length of 27. And now the longer of the two sides on the green triangle is PQ, which has a length of 18. So this is the ratio. These are the two ratios that I'm going to check to see if they're equal to decide if SAS works here. So 18 over 12, I'm going to notice that I can divide both of those by 6, and that gives me 3 over 2. 27 over 18, both of those numbers can be divided by 9, and it gives me 3 over 2. So we're good. We have our one pair of congruent angles, angle Q, and then the sides that include those angles get set up into this proportion here, these two ratios, and those two ratios are equal to each other. So we can say that yes, triangle PQS is similar to triangle. Now we have to be careful here. PQS would be similar to RQP. I guess it's the way that they were listed up there, so that makes sense. RQP by side angle side similarity. Here we have one more example, kind of a bit of a convoluted picture here. We have, actually I see 3 different triangles in this picture. And first we're going to ask ourselves, is this triangle, ADE, similar to this triangle here, ABD? So again, our options to prove that they're similar would be to use angle, angle, side, 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 or side, angle, side. And I like to look at the information that we have for the two triangles to kind of guide me towards maybe trying one of these 3 things. So in triangle ADE, you'll notice that I have lengths of all 3 sides. I also have one of these angle markings here. So I have lengths of all 3 sides and an angle marking. In ABD, I have lengths of all 3 sides. No angle markings though. So that kind of guides me towards checking to see if SSS works. Can I set up the ratios of the corresponding sides and show that they're all equal to each other? And if I want to know which sides to set up in the ratios, I look at this similarity statement and I say, okay, AD needs to be in a ratio with AB, and DE needs to be in a ratio with BD, and AE needs to be in a ratio with AD. And again, the way I picked out those pairs was I looked at the placement of the letters in this similarity statement. AD and AB were first 2 letters, DE and BD last 2 letters, AE and AD first and last, first and last. So now let's substitute actual side lengths for these measurements here. And that's going to be 2.4 over 3.2. DE is 1.8 over BD, which is 2.4. AE is 1.8 over AD, which is 2.4. So first of all, we can see that these 2 ratios are clearly equal because they're identical to each other, the same numbers. So what we really want to check is, does this ratio end up equaling either of these 2 ratios? Now, when we start mixing decimals in with fractions, it does get a little bit tricky. So I'm going to take this 2.4 over 3.2, and I'm first going to multiply both of these by 10. The top and the bottom, because what that's going to do is going to move the decimal place over by 1 to get rid of the decimal. I'm clearing the decimal out of there. So that's going to give me 24 over 32. And then I'm going to do the same thing with 1.8 over 2.4 and turn it into 18 over 24. So now I have, instead of 2.4 over 3.2, I have 24 over 32. and 1.8 over 2.4 became 18 over 24. Just multiplied all the numbers by 10. And so now I'm going to reduce them. 24 and 32, I can divide both those numbers by 8, and it gives me 3 over 4. 18 and 24, I can divide both of those numbers by 6, and it gives me 3 over 4. So you can see these two ratios are the same. These two ratios are already the same because they're identical. So that tells me that yes, by side, similarity, I have these two triangles similar to each other. Next we have, is triangle ADE similar to triangle BDC? And so here we have, again, triangle ADE, where I know all three sides and I have an angle marking here. But then triangle BDC, I only know 2 of the side lengths, but I have that same angle marking here. So that kind of guides me towards checking to see if SAS works. And so if I look into that, I can see that, okay, so far I have angle ADE that I know is congruent to angle BDC. So that takes care of the congruent angle pair that I need for SAS. So now let's just set up the angles that include those, or sorry, the sides that include those angles. Let's set those up in a ratio. That would be maybe AD over BD, and check to see if that equals ED over CD. And so when I substitute in the numbers for those, the actual values, I have 2.4 over 2.4 equals 1.8 over 1.4. Now something seems off here, right? Because if 2.4 is over 2.4, I know that's just going to end up equaling 1 over 1. But 1.8 over 1.4 does not equal 1 over 1. Does not equal 1 over 1. And so that tells me that no, not similar for these two triangles. Yes, they have the pair of angles that are congruent, but when I looked at the side lengths that include those angles, they're not proportional to each other. When I set up these ratios, they don't equal each other. So we're going to say that they're not similar.